Science, and also one of the organizers of this lecture series. On behalf of the Engineering Science Department and the School of Science and Technology, I would like to welcome you all to this fourth lecture of this series this year. Also, I would like my thanks go to Agilent Technologies, who has been sponsoring this lecture series since the start. Before I introduce our guest speaker for today, let me mention that on the 4th of November, we have another interesting talk titled Application-Driven Network Transformations by Mr. Richard Lopez. He's the director of Packet Technology Product, Scion Optics. For the lecture today, the title of the lecture is It is Good to Live Near a Star, an Introduction to Photovoltaic Energy Production by Mr. Paul Herndays. Paul Henry is an application engineer with Solmetric Incorporated, a leading manufacturer of electronic and software tools for photovoltaic system designers and installers. Paul's current professional focus is on the measurement of photovoltaic array performance, particularly during commissioning of new photovoltaic systems and maintenance of older systems. His background is in the development and application of electrical test instruments at Hewlett-Packard and Agilent Technologies, and in the design, installation, and testing of photovoltaic systems. Paul received a Bachelor of Science in Electrical Engineering from University of Wisconsin and a Master of Art in Organization Development from the Sonoma State University. So here is Mr. Hernday.
Thanks, Bobby. Thanks, Ali. It's really nice to be here, and thank you for coming. I know you all have busy schedules, and I have to say it's kind of it's an odd moment for me because I've never given any kind of a presentation to a university group before, and I kind of feel like my life is telescoped, and I'm back in University of Wisconsin, sitting where you're sitting, listening to somebody who came before me, and who it's all just sort of like one big cross-fertilization effort. We're always working on the backs of other people that came before us, and it's nice to be part of that chain. So Ali gave a little bit about my background, and I just want to mention also that if there are any people here who are interested in careers and would like to talk afterwards, if we don't have enough time, we would like to take some more time to talk about careers and finding jobs and things, I'd be happy to stay afterwards. So please ask any questions, tell any stories, or whatever you want to do during the talk. Don't hold to the end, okay? And I kind of organized it under the concept of just PV as an energy source, and there are a lot of other sources that I'm not going to talk about. Just that one's enough, and but it's only one chunk of renewable energies. And just to start off by saying it takes about 10,000 years for a photon that's formed at the beginning at the center of the sun to work its way out to the surface. About 10,000 years on the average. And you can imagine how motivated it is when it gets to the surface. I want to do good, I want to do something. And then it takes, I forget, 5, 8 minutes, something like that, to get to the third rock. And then it's up to us to do something with it. It's not going to be wasted. It's going to keep the Earth in balance. But if we're creative, we can really get a lot of power out of it. And that's what I want to talk about today. By way of introduction to Solmetric, we produce test equipment and software for evaluating sites, getting the shading characteristics of sites before design, and then designing it. We have software for doing that. And then finally, we're just introducing now a product I've been working on for 2 years, which measures the PV arrays in the field, their electrical characteristics. So these are the topics, and I'm going to try to get through them all. It's about 100 slides, and some of them are just picture tours, so they'll go by really fast. So don't panic. And but if it does begin to feel like death by PowerPoint, at some point just sweat or raise your hands or say something, and I'll just jump over some pieces of it. Are there any pieces in here that you particularly would not be interested in covering tonight, be hearing about? Or does that seem like it would work offhand as an outline?
Yeah.
Should we try it?
Yes.
Okay, let's do that. So just a few slides by way of perspective of solar in the energy mix. In the U.S. today, solar is less than 1% of our renewable energies. And our renewable energies is only 8% of our total energy consumption. So we have a long, long ways to go before we can power the country, even our electricity demand with solar. And so even though solar seems like it's a big gorilla right now, you read about all this growth, it's still really, really tiny. And renewable energy makes up about 8% of our energy budget today, but only a little bit of that is solar, and most of the solar, all of the solar goes into electric power, whereas a lot of the other renewable energies goes into transportation, fertilizers, industrial heating, and things like that. But the positive side is the growth is really significant. We were talking about exponential growth before we started here, and it's been exponential for a long time, but you know, the way exponential curves are, you keep changing the scale factor and it looks small again. But we've got to trust that it's going to keep growing over to the right, and we'll just keep changing the scale factor every year. One of the things to notice is that utility is starting to grow at the top. Utility, the yellow, and some policy changes that are bringing utilities on really strong. There's a lot more PV systems in Germany, Spain, and Japan than there are in the U.S. We're way, way behind. Again, on the positive side, we have a lot of solar resource. The red area is just really high hours of sun per day, and a lot of wind as well. The center part of the country is really windy, so it's good to live in West Texas, because you have both sun and wind. Another good thing is as production of PV modules is going up, the cost of PV modules is going down. It's around $2 a watt now. It's really, really dropped. So how does PV work? This is a grid-tied PV system with solar panels on your roof or in your backyard or on a factory roof. There's an inverter that changes it from DC to AC. There's an AC load center, which is pretty much your switch box, and then a meter, your existing switch box. And so whatever power you don't use in your house flows into the grid, and you get paid for that each month and at the end of the year. Each of those PV modules is made of PV cells, and so at the top is a cell and a module made of, say, 72 cells. And then the modules get grouped together into an array. And right now we're going to focus on the cell and how the cell works. And Don could explain this a lot better than I could, because he's a semiconductor guy. But let's just say you have two differently doped pieces of crystal and you slap them together, or you take one crystal and you dope them differently on two different sides of the dotted line. And what happens is that you have a slight excess of dopant electrons on one side and dopant non-electrons on the other side, holes. And so the electrons and holes diffuse into the other side because there's lots of space over there. And that forms an electric field across the junction. And if a photon comes in and creates a charge pair, if you're lucky, one of them gets swept across that junction by the electric field, migrates its way over here to this contact, and gets collected and goes through the external circuit. And when it comes back, it cancels out essentially its opposite charge, which has drifted over to this contact in the meantime. It's a beautiful, beautiful effect, and it's all because of the built-in electric field that we get practically for free. It's just an amazing, powerful concept in the world of energy. And so I made the mistake in a talk a few weeks ago of saying that was really easy to do, and there were a couple of solar cell designers in the audience, and they totally set me straight on it. It's not easy to do, especially when you're making diodes that are 6 inches across. It takes really high purity material to do that. So this is, for those of you who are in electronics, this is the equivalent circuit of a solar cell. It's a constant current source. it's driven by the sun, the more irradiance, the higher the current, shunted by a diode. And if you open circuit it, then all the current goes through the diode, and a certain open circuit voltage results. If you short circuit it, all the current goes through the short circuit, none through the diode. And in between you have kind of a diode sort of knee effect. And so that curve over there, that red curve, is the IV curve, current voltage curve, of a typical solar cell. And there's a point on that curve that corresponds to the maximum power that it can generate. So this is not a passive device. You're used to seeing passive curves up in that quadrant of the IV curve, but this is actually sort of flipped around and so that it's a generator. And that orange point on the knee is the maximum power point.
Would that point determine the resistance, that resistor that we need to put across this diode?
It does, exactly. If you draw a line from the origin through that orange point, that would be a resistor value, where you could load it perfectly at that point. And that's kind of what the inverter does. It creates a load that keeps it operating at that current and voltage pair. So there's the maximum power point in voltage and current. And the job of the inverter is to adjust that point on the curve so that that gray area is as large as possible, because that gray area has the units of power. It's voltage times current. And so if you multiply voltage and current on that curve at every point, you get this blue curve. That's the PV curve, power versus voltage. And the inverter's job is to stay at the peak. Now, anything that damages the peak damages the power output. So anything that makes the curve look funny is going to bring that peak down. The way I like to think of cells in series and parallel, like an array or a panel of cells, is to just imagine the IV curve of a given cell added in series. If you're putting them in series, you get more voltage, and if you put them in shunt with one another in parallel, you get more current. And the end result is you have a curve that looks exactly like your starting curve. It's just scaled up in both directions. And
Can I ask you a question here? Now, when you put in parallel, then there would be some internal current through these things, right? Wouldn't it be wasted, that current?
No, actually, they just act like batteries. They just combine in parallel. They're current sources.
Yeah.
And so the only reason that there are a couple of cases where you can have that. If there's damage to one or the other, then current can flow backwards. But usually, if it's a healthy array, it's fine. So in the presence of shade or other sorts of damage to the cells, you can have a case where the IV curve has, like in red there, has a kink in it. And now it has two knees. See, over on the right-hand side, it has two red knees. And each of those red knees corresponds to a local maximum power point. And so that's why you have two bumps on the blue curve. And the inverter has to check around to find out which of those is the highest and track the highest one. But if that's caused by your willow tree and the wind is blowing, the shade, then the peaks are moving around and the inverter's going, where's the peak? You know, it just can't find the peak. So you lose a lot more power than you'd think. These are array performance factors, everything from climate, which determines how much sunlight you get, down through soiling and shade. Turns out you can lay out your strings in a special way that's less vulnerable to your particular shading pattern, but we don't need to go into these. Just to let you know that there are a lot of factors. Are there any questions at this point? Just go ahead and jump in if there are. So this is a quick picture tour of what PV systems look like. And it's differentiating like mad. There are just so many elaborations on the concept of a PV cell. It's mind-boggling. And the first one you're familiar with already is flat plate PV. And what's meant by that is just flat solar panels that you put on your roof, or you'd see on a factory top, or on a pole, or sometimes you'll see them on a ground mount, a pipe frame that has these things mounted on them. Each one has 72 cells typically, and they're all connected in series. In a big system, there'll be many strings. This might be one string of modules, meaning that they're all connected in series. Each has two cords on it, and you just pop them together. This one might have, this might be a string, this is a string, this is a string, this is a string. So many strings in parallel, many inverters in that system. Yes?
I've seen people that have the panels on their roofs, they like to have them facing the sun.
Uh-huh.
If it's on the other side, how much is it, does it affect it
You lose a lot.
drastically?
Yeah, if you're pointing north, you're gonna lose a lot. I was mentioning earlier that if you don't have a south exposure, if you could do southwest or even west, it's still practical. But if you get north of west or north of east, then it's probably not worth it. However, if you only have a north-facing roof that's open to the sun, you can still put modules there by building a scaffold or framework that tilts them up from the roof, look over the ridge. This is a system I visited in Oregon recently, 7 inverters. That's Mount, it's in Portland, so would that be Mount Hood? Forget. Anyway, it's across the Columbia River. But there were 7 inverters, and each one serviced a piece of this huge, huge array. And this is that, there are yellow stripes across it. And this is looking down one of those stripes into the parking lot. You can imagine what it felt like to stand up there on this array. You kind of felt like if you stumbled, you'd just keep on rolling right down into one of those cars. And then those 2 silver dots in the middle of the yellow platform, the yellow walkway, are combiner boxes. And combiner boxes are a fixture in big systems. You always have them in the array itself. And that's where all the strings, all the wires from the ends of the strings of solar panels come into these boxes. And this is what it looks like. You have, so this is 2 feet wide roughly, and these are the big wires that are going out to the inverter, really heavy like battery cables. And these are individual string positive leads that are coming in, here and here. There are 23 of them in this case, and 23 negatives that go to this in here. And all the negatives are collected on this metal bus bar and go out through these 2 wires in parallel. And all the positives go through touch-safe fuses that you can pop loose without hurting yourself. Each of these is a fuse. And they get collected by these 2 bus bars, which are wired to these 2 red leads and go out. And that's the basic concept. It's no more complicated than that. All you're doing is adding things in parallel.
How many volts do you have per module?
Typically, modules are 30 to 60 volts, something like that. And so you can put quite a few in parallel before you get to the 600 volt limit. US PV systems, except for certain utility systems, are always 600 volts or below. So the next, oh yes?
What happens if you go over 600 volts?
If somebody catches you, you could lose your license as an electrician or an installer. Yeah. Also, you could start a fire because insulation could break down, things like that. So the next part of the tour after flat plate is concentrating PV, and this starts to get really interesting. The simplest of them is a module that has a little ribs in the glass. Usually the glass is just flat. It may have a little texturing to reduce reflection, but in this particular one from Solaria, the glass has bumps to it, and they're cylindrical lenses basically cast right into the glass. And that causes the light to come down parallel and focus in kind of on a line. And then they put silicon solar cells only where the light is focused. And that allows them to use a lot less silicon because they can leave spaces in between those silicon strips. And this is a low focus, a low concentration solution. It's only about 3 or 4 times concentrated. But
Does that work when it's not tracking the sun?
it has to be tracked. It has to track. Otherwise, it's worse than a regular panel. So that's the lowest concentration. This is the next concentration level. These are trough reflectors. And these are big sheets of aluminum with a slight bend to them. And they form, if you look at it from the end, they form a W like that. And each of the blades of the W is a reflector. And each face of the aluminum bounces light up to a strip of solar cells at one of the other apexes. So if it bounces here, it collects here, but if it comes in and bounces off this, then it collects here, or here, or here. So, and then they can just use a thin strip of PV cells that are much smaller, and they can be replaced. You can pull them off and put a more advanced strip on someday when better cells are available. So So that's cool. This company uses Fresnel lenses to focus down on a chip. Actually, in this case, there's no depth to it. It's a flat plate, and it's light guides, so the light comes in and turns the right angle and goes to the chip in the middle. It's pretty amazing. I can't imagine how it works. This is the typical Fresnel lens in a box solution. A big collector, big tracker, and each of the cells has a Fresnel lens that focuses light down on a very small solar cell chip. Here's another one from a different company. These are big. These are really big, and they have to track within a quarter of a degree. This is another Fresnel lens in a box solution. It's small enough to put on a rooftop. It's designed that way. Similar with this one. Just different companies. I just wanted to show you the sheer breadth of solutions there are in this area. And those of you who are involved in mechanical might notice that, tracking these things is a pretty interesting problem. Yes?
Do the concentrated panels just reduce cost, or do they actually produce more energy as well?
They mainly are intended to reduce cost because of the fact that they use so little silicon. And they were started back in the days when silicon was really expensive, and at that time they had a great advantage. But now that silicon is in great supply, its cost has dropped through the floor, and these guys are not quite as advantageous as they would have been. But they do have some terrific advantages. One is that since they can track throughout the day, you don't have a bell-shaped curve of production. You have a curve that comes up quicker, stays flat longer, at the peak longer, and then it drops off. So it's much broader, and you can get 25 to 30 or even 40% more power with these guys than you can with flat plate collectors.
What about cloudy days?
On cloudy days, you don't get anything from them. They require direct normal radiance, yeah. So you'll only see these in states that have clear weather most of the year and very little local fog, and only when you have a really good skyline, no trees or buildings nearby. Because to get the best effect, they have to track from early morning till late afternoon. Another version of that. Just to mention before I finish this section that these types of concentrators typically use a multi-layer silicon cell or gallium arsenide or some other system. But the purpose of that is that an ordinary silicon cell can only process a certain part of the wavelength range of the light coming in. And so if you have several junctions in series, each one of them tuned to a different light wavelength, then you can collect more of the power. And as long as you're investing all this energy in a tracker and lenses and stuff, why not put a few more bucks into the multi-junction?
Do you have a rough number for how much more expensive?
I don't.
Because it's got to, that many layers in MBE.
Yeah.
It's got to be very expensive.
Yeah. So the plus is that you can make it in some pretty small chips.
Yeah.
And it's your yield is better.
I mean, it's a great idea, but it's
Yeah.
got to be expensive.
Yeah, no doubt. Yeah. And just to point you to this, I won't go through it, but this is NREL, the National Renewable Energy Labs, publishes every year the best research cell efficiencies for solar cells. And the ones that are up at the top, the purple ones, are always the concentrated PV ones. The ones that are built with these triple junction chips and lots of concentration. The concentration on some of these systems can go up to 650 suns. Imagine that, taking, if you ever burned ants when you were a kid with a magnifying glass, don't pass that one on to your kids. But
So what's the maximum temperature?
you can imagine you got, I don't know how many suns you got from that, but 500 suns, 650 suns is a lot of power.
So if you are talking about like 40 to 44 efficiency, right? So
You can get it into the high 30s and even into the 40s.
Yeah, which is good. Yeah, because
Whereas flat plate collectors are going to limit out somewhere in the low 20s.
Right.
And then I thought I'd show you a few pictures of solar thermal. My apologies to any thermal engineers in the group, but I'm biased towards PV, but these are still so cool. These are power towers. They're usually put out in the desert or way out in the country someplace. And there are thousands of mirrors on big trackers, just plain big mirrors. And they follow the sun and they focus it on a tower, on a boiler at the top of the tower. And they're so powerful that if it's a partly cloudy day, they can't even focus because the change in intensity of the light, they change from hot to cold, would just shatter the top of the tower.
That's a functional unit?
It is, yeah, it's in Spain. And this is another version of it built in a modular fashion so that you can put these cells, a single power tower and a certain number of reflectors, plop it down. If you want another megawatt, you plop another one down. It's a lot easier to deploy. And then solar trough compensators, you run a tube down the focal point of a solar trough, a parabolic trough, and you run like something like glycol or antifreeze or water through it, and it heats it up, and then you drive a turbine with that. Or you melt some salts, and you store the melted salts in a big insulated container overnight and draw power from that by running a turbine from it. And these are being deployed all over the place in the deserts now. These are Stirling engines driven by a dish as the heat source, and they can be either an automotive type 4-piston engine that uses expanding hydrogen or helium to push the pistons, or they can be what they call a free piston design that has only one cylinder and one piston. And as the sun heats the hydrogen in it, it causes the piston to vibrate back and forth. And the other end of the piston is connected to an alternator, just like on your motorcycle or your car. I guess maybe in the old days in your car? I don't know. Anyway, it generates electricity, AC, so it's very cool. And these things are very efficient, and big fields of these are being deployed as well.
And then now here, since we are talking about reflection and so forth, shouldn't these now be very clean, because if there is a lot of dust on them?
Yeah, they should, because of the light will scatter from the dust and then it won't be collected.
Right.
But the whole industry as a whole is downplaying the effect of dust. And the argument I heard yesterday at a conference is that there are a lot of hotels that are out in the desert. You don't see their windows always covered with dust, and you don't see them all pockmarked with pit marks. So glass is pretty tough, and it takes a pretty intense sandblasting to do them in. So plus, if they have a dust storm, they can tilt these things so that the dust tends to go across them rather than into them. They can tip them away from the dust. There are a lot of strategies. And then afterwards, if they do get dirty, they can tip them upwards and just run a hose truck by it. And they just spray them and the dust runs right off. So let's take a quick look at the solar resource. If you had a home and you were thinking of putting PV on it, or even a thermal system to heat water, you'd want to know how much sun power you were getting. And part of it is weather, and part of it is obstructions in the way, like a chimney or a tree. And the sun pads always look kind of like this over the year's time. The high ones are in what season of the year? Summer. And the lower ones are in the winter, where it's closer to the horizon. And the peak of all those curves is solar noon. Whatever the time of day is, that's solar noon. It's usually within an hour of noon. And so it turns out that each one of those cells, defined by the hour of the day and the month of the year, has a certain amount of solar energy in it. And you tend to get more at the top cells, in the middle of the summer when the sun is high overhead. And it turns out that the National Weather Bureau has extensive history of this. And we can get data on the amount of solar energy available almost anywhere in the country. The insolation is the amount of solar energy per unit area, and usually in watts, kilowatt hours, or watt hours per square meter. So if you had 1 kilowatt per square meter irradiance for 6 hours, that would be an insolation or energy of 6 kilowatt hours per square meter. And if you had an array collector area that was 2 square meters, that means you'd get 12 kilowatt hours. And so the first thing to pay attention to in designing a PV system is which way are you going to point the panels, your PV array. And if you start with this much energy from the sun, say this is proportional to energy from the sun, you have this annual insolation or energy that you have to work with. If you're always going to lose a part of it, or sometimes you lose a part of it because it's not pointed in the right direction. Your array is pointed a little bit too far east or west or something. And that leaves something else that you have to work with yet. This remaining percentage is called the TOF. The percentage is the tilt and orientation factor. And depending upon where you live in the world, you may want to point it south or something else. This is a curve from Honolulu that shows that the sweet spot as far as tilt and compass direction is at about a 25-degree tilt and 150 degrees. So that's quite a bit east of south. And that's because they have afternoon thunderstorms, afternoon storms in Hawaii a lot. So you want to look at your local map. And by the way, this is live on the web from Sometric. So if you ever want to find out where the sweet spot is for your house, you can look it up. And then the next thing, which is really the killer in PV systems, if you've done your tilt and orientation right, is the loss due to shade. So you take what's left after setting your modules up, and then you lose part of it due to shade. Whatever is left is what's available to actually turn into energy. And just to communicate how bad shade can hurt you, this is a friend's PV system. And what we're looking at here is power output vertically versus time of day for different seasons. And in the middle of the summer, he gets a nice bell-shaped curve where he gets good power production right from early morning to late afternoon. Whereas in the winter, the walls, he has straight walls on the sides of the peak. Notice how that red curve it's bell-shaped for a while in the middle and then it drops like a rock. And that's because there are stands of eucalyptus trees to the east and west, and the sun comes out of the side of that stand in the middle of winter, whereas in the summer it goes over the top of them. So shade is really, really important. And just to finish this series, down at the bottom there's a factor called TSRF, which is a percentage, and that's just the product of those other two percentages. So if you lose 10% of your production to the tilt and orientation being not quite right, and another 10% because of shade, then you're down to 80% total solar resource fraction. And these two instruments are manufactured by Sometric right out here in our own Sebastopol. We are the world's leading manufacturer of solar shade analysis tools. And we're very happy, very, very happy and grateful about that. The company was started in 2005 by a local engineer from HP that a lot of us in the company worked with. He had a solar system installed on his house and it didn't work right, so he had the installers come back and redo the shade measurements. And they said, no, it should work fine. So he said, there's got to be a better way to do this. And so he put together a quick prototype of kind of a mechanical shade analysis tool, and it led to this electrical one. And it's really great. So the way this works is it has a fisheye lens on it and a digital camera behind it. So it takes a picture of the entire sky right down to the horizon, as you see in the upper right. And the trees all look like they're upside down because they're coming from the edges of the shot towards the center. And then the software, as shown in the lower left, automatically determines from contrast ratios what's shade and what's open sky. And then it goes through every little pixel, every 1 hour segment of the year, and figures out, okay, I know what the weather is, I know what the incoming energy is from the sun, and is this clear or is it shady? And it makes that decision and it puts it in one bin or the other, shaded or gone, or coming into your system. And at the end, you have a bar chart, like in the lower right-hand side, that shows the solar axis. In other words, the effective shade for each month of the year. And that is an awesome tool for figuring out exactly where to put your solar system and how much energy
So
you're
how
going to
long do you need to put the device, the measurement device there to get an idea of?
Well, the nice thing about it is that since it has all the sun pads and the weather all stored in it, all you need to do is click it, and it has the whole year worth of analysis done in about 20 seconds.
Okay.
So just one instant, yeah, to cover the whole year. And then briefly, I'd like to talk about how PV arrays are measured. This is actually something I'm working on now, the new product that I mentioned. You can measure PV arrays the simple way by looking at the inverter and just figuring out, well, it says it's producing 2 kilowatts. Is that what I bought from the installer? And you look at your contract and it's, oh, 2 kilowatts, so it must be working right, which is kind of a pretty rough indication. In a large system, you could have lost a couple of strings of PV modules and you wouldn't even notice it. It would be like 1% or 1/10%. So you can use electrical test instruments like the two in the middle to help with it, or you can go all the way to the right and use a more sophisticated technique like a curve tracer. It traces out the IV curve that I mentioned earlier. And then if there's anything wrong with the system, it would show up in that curve. And that's what we're working on. And it gives you a lot more diagnostic value, and since it's automated, there's very little chance of making a mistake. It'll point out if you have series losses due to something getting resisted in the string, then the right-hand part of the curve will slope inwards. And if you have losses, leakage through the cells, then the upper part of the curve will slope downwards. And you can measure that very sensitively. And the instrument itself is done by the measurement is done by loading the output wires of the array or module with either an electronic load like a power supply or a current sink, or putting a decade resistor box there and switching all the resistors to work through the curve. Or like we do, we put a capacitor across there and charge the capacitor. And in any case, what you do is you change the operating point and you keep measuring this pair, current and voltage, at each operating point along the curve. And built into our instrument is a set of models, 3 different models that are one of them is quite sophisticated. The middle one's not so sophisticated, the bottom one is downright crude. But one way or another, no matter what your PV module is that you're putting on your roof, we always have a model that can help you check whether it's working right. And that's what the instrument looks like. It's a soft case, has a soft case, you can sling it over your shoulder, has a wireless interconnection to your laptop computer or notebook or slate, whatever. So that you can walk around actually doing tests on, you can shade panels with your hat to try to determine which part of the panel is dead while carrying your computer around and actually, wirelessly getting your measurement updated all the time. So it's a very cool instrument. This is one of the outputs of the instrument, one of the screens. If that bar reaches the target, that means you're getting 100% of the modeled power and the string is okay. If it's not okay, you can look at the other screen, look at the curve itself and see if the curve is distorted by some problem and then troubleshoot it from there. A couple of quick measurement results from this, and then we'll move on to some other stuff. This is a field-aged thin film module. Thin film is done differently than the crystalline squares cells, and they tend to age quicker. This has been in the field about 12 years, and it has both series and shunt problems. So the curve is pulled away from the model points and has lost a lot of its output power. And yes?
How long does an array or panel last, time-wise?
They need to be, according to the California Energy Commission, they need to be guaranteed for 25 years at least it is. And the specifications usually require them to lose no more than, I forget whether it's 0.5 or 1% per year. I think it's less than 1% per year in production.
And is there a certain type of maintenance that you need to keep up on them?
Right, that's a good question. The maintenance is, the obvious one I guess is keeping them halfway clean. A thin layer of dust will only lose less than 1% of energy. But if it's starting to get covered with thick layer of dirt, like somebody just plowed the field next to your array and it just collected like mad, then it's time to wash it off, because it could be 4 or 5%. The other thing that causes them damage is when lichens grow around the edges of the glass. So you want to keep your eye on that and scrape those off every once in a while. But otherwise, maintenance is pretty simple. Just clean them.
Do you just clean them with water? Is it that simple?
Just clean them with water, and the only caution there is to make sure that you don't put cold water on hot modules or hot water on cold modules, because the glass could crack. And I always use a fine spray so that by the time the droplets get to the module, they're small and they're at air temperature.
Yeah, and the birds and squirrel and so forth would not, we don't dare, they don't dare to
I was servicing an array when I was working as an installer, and it was on this really steep house. I had to use my climbing gear, you know, what you'd use on a vertex wall or something like that, to get up the top of the roof. And they had the modules coming up over the crest of the roof, about 4 feet. So I was going up the north side, and I got to the modules, and I put my hand over the top to grab the top module and pull myself up. And it turns out that birds had been standing along the top of this row of modules, and the top 6 inches was like a ½ inch of bird dung. So, and his modules weren't producing anything, because what that did is it shaded the top row of cells, and that killed the current through those columns of cells. And so, yeah, birds are a problem. An individual bird dropping is usually not really big. Like a robin might produce a dropping. A robin might be like that, but I mean, if you're talking an osprey or an eagle or an owl, I mean, if you think of a Hostess Twinkie and then you never saw Ghostbusters.
So there need to be maybe some way of avoiding these give them away or whatever.
Yeah, some people will put little fingers along the top of their array so that pigeons and things can't sit on it and decorate the module. Yeah. But the trick is to get the birds to cover the array in a thin, widely spaced pattern so that it doesn't stop any one part of the array. Then you can just clean it off once in a while. So I'd like to show you the effect of shade on PV arrays. I mentioned that you can stop a whole string of cells by blocking one of them completely. This is a module, a PV module, and it has 72 cells in it. Each one of these is about 5 or 6 inches square, and they're all in series. And typically they go down, and then they're connected down here, and they come back up. It's like putting batteries in a tape recorder or something. They connect, they go down, and then they come back up. And then they keep doing that, so they're all in series, 72 of them. And to prevent damage to these guys and to minimize the effect of shade, they put regular old diodes across, spanning each one of these cell strings, as they're called. So if you shade this cell, the rest of the array will actually try to flip the voltage on this around. And to protect this cell, this will actually turn on. And it'll just conduct the rest of the current from the array right past that cell string. So what that means is that even though the unit of production is the cell, what you observe in an array when shade hits it is it tends to drop out in quanta of what is this, 24 cells. 24 cells, whatever this is, however many cells. It's one cell string at a time, which may be 18 volts, for instance. So you'll see suddenly as you shade one cell that, boink, I lost 18 volts in my string. And that's because this entire group of cells just dropped right out when this turned on. In the early days of solar, without those bypass diodes, the shaded cell would just burn up. And the glass would crack and sometimes a fire would start. Did you have a question?
Yeah, I was gonna ask, like the way that they're like engineered, like arranged on your roof or whatever, is it pretty sturdy, would you say? Like,
Yeah,
it
it's very stable. These things are tested, by the way, they put sandbags on them to make sure that the glass will hold up. They fire hailstones at them out of cannons to make sure that they'll take care of that impact. They don't do golf balls very well, and they don't do ball bearings drop from airplanes, but otherwise they're pretty good. And as far as ruggedness on the roof, they're typically mounted. If this is the edge looking at a PV module, there'll be an aluminum rail like this, usually mounted about 20% in from the edge, and then some clips that go over the top of this and hook them down into the rail. And these guys usually are supported on some posts that they have little feet on them, and these are screwed into the rooftop. And then this whole thing is covered with a weatherproof jacket. And there are very strict requirements from the manufacturers as to how often you have to put those standoffs to make sure they don't come off the roof.
There's a building on the other side of campus, I can't remember what it's called, but it's like got a green roof except black solar panels, it's like solid black.
Okay, I haven't seen it.
I wasn't sure how that would work, like, cause it doesn't have the squares on it.
Oh, okay. I'm glad you asked that, because I totally forgot to mention that. There are panels that look like that, and you'll often see that they don't have these white lines, but you'll often see these white diamonds at the corners of the squares. I kind of accentuated the distance because I wanted to show that these are individual cell strings. But the diamonds are the typical way. They look kind of like this. The other one, and this tends to come from SunPower and a couple of other manufacturers, is that the cells are actually perfectly square and there appears to be no distance between them. And the cells are black, and they put them on a black back sheet so that you don't see the space in between them. And the reason they can be totally black is they don't need these wires. These are actually thin silver, baked on silver conductors that collect the charge from the front, and they bring it to this central wire or pair of wires. And so that's got a contact on the front and another one on the back. And SunPower's modules are back contact modules. So both contacts, if you look at it this way, on edge, both, the current coming in and the current going out are both on the back side. So you don't need collectors on the front, and they're perfectly black. They're really simple looking. Yes?
Would you say that that's like a more, would you say that's a more effective way, like with all the other stuff in it, like?
It turns out that the SunPowers are they're the highest efficiency modules on the market today. The average is about 16%, and if you look at 30 manufacturers on a chart, they'll all be at 16%, except Sanyo and SunPower, which are at like 18 or 19%. So they're the classiest, probably one of the most reliable and certainly the most efficient modules. So why would you do that? If you have a lot of roof space, you only need 2 or 3 kilowatts. Why would you bother with that extra expense? But if you have a really small roof and you want to get as much power as you can, then maybe you're willing to pay a premium for those panels that are more dense, get more energy in a smaller area. I mentioned earlier that shade can cause a couple of bumps in the power curve. Just wanted to remind you of that because I'm going to show you some shading measurements now. This is a current voltage curve where I put my business card on one cell of a string of 15 modules, each of which had 48 cells in it. And does anybody do multiplication in your head? That's a lot of cells. And a business card, just a business card, and one of them caused a couple % drop in the energy. So it's really, really sensitive to shade. And you don't want to have shade on your array. This is the shadow of a leafless branch that I put on a module the other day. Can you see the shadow of the branch on the module itself? It's kind of hard to see, but they're very thin. It's only about as thick as your finger. And it dropped 5 or 7% of the efficiency of the module. This is a system we troubleshot last week with a local installer, and he was convinced that shade wasn't enough to screw up the performance of that string. And we kept making string measurements with our instrument, and every time we measured it, the curve changed. And it took us a while to realize what was going on, but it was windy. That was a willow tree. Willow trees just dance, when the wind is blowing. So every time we got a different shading pattern. And this was a typical curve. Now the dots show where the curve should have gone. So he was losing huge power from that system. Now in this, I did a couple of experiments just to sort of tutorial value. This is a single module measurement, and this is a cell string. Current's coming down, and then it's coming back up again, right? And then at the top is a bypass diode, and if you shade it anywhere, it'll switch that bypass diode on and bypass that piece of the module. There are 3 of these cell strings in a module, so if I block one like I did with this piece of cardboard, I'd expect to lose 1/3 of my voltage, which is exactly what happens. This should be the open circuit voltage. Instead, it starts here. I get what looks like a normal IV curve, but it's only at 2/3 the voltage. It's a normal current, though. And that's what's nice about those bypass diodes, is they don't interfere with the short circuit current. They still let the full current flow. They just kick out some voltage range. Now, if I take that same piece of cardboard and I turn it at a right angle so that it's not just on one cell string, but it's covering 2 cell strings, then I lose what fraction of my voltage? 2/3. Because there's now only one cell string that's still performing. Are there any questions about any of this measurement stuff? I know that's getting a little esoteric for tonight, but yes,
So essentially, if you were to block out the third one,
that module would be gone.
so you essentially get no current or voltage from any of the other panels?
If I block the third one, suppose we're talking about a string of modules like this, or panels, and each one has 3 cell strings in it. So if I block one cell here completely, it's gonna just, the current from downstream is just gonna skip that one, go across it to this one. And if I block a whole panel's worth, then all 3 of the diodes at the top are gonna turn on. And this panel will be bypassed altogether. The current from this one will go into that, and then it'll go into that.
Now, blocking the sun basically can come from either shade or maybe dropping of the bird, whatever.
Right.
So this means that the maintenance should be really, periodic, so that.
Yeah, it should be periodic. I mean, if it were my array, I'd clean it maybe 6 times a day at first. Just because I put $10,000 into it, and I love PV. But I'm sure that would drop off after a while, and after a while it'd be once a week, and then it'd be once a month, and maybe I'd forget about it for a year, and then it turns out it'd be really dirty. And somehow you'd find a right timing for checking it. But I would think looking at it once a month is probably a good idea. Just look at it with binoculars or something if you can't get close to it. And if it's dusty, consider every few months cleaning it off. If there's bird poop, then you might have to get up there, because sometimes that's pretty nasty. Should we talk at all about jobs? Trends in the industry? Yeah. So, the industry is, this is not just about PV, but in general, the industry is very policy driven. It's totally policy driven. If we didn't have government sponsorship for incentives and rebates and tax credits, we wouldn't have a solar industry at all today. So it's, if you ever think about getting involved in politics or whether your vote counts at the election time, the solar industry could disappear if we don't have political support. So I visited some of the national labs and talked with some of the researchers who are dedicating their lives to making this a reality, and they're terrified that we're just going to have political swings, and parties will come to power that won't support solar energy, and we'll just lose it. And it would be a shame, because other countries are shooting way ahead of us as it is. We've got to catch up ball game on. So what we've seen is that the picture disappeared. Is that going to come back? Okay. So in this state and in a number of others, we've seen the coming and going of incentive programs. They pop up like mushrooms. Sometimes they're way too lucrative. Like in Germany, they were giving 70 cents per kilowatt hour, something like 4 or 5 times the normal cost of energy, for people to put solar on their roofs. And then Spain did the same, something similar. And then there comes a time several years down the pike when that has to be financed out of utility rates. And so the rest of the ratepayers that don't have solar start to go on the warpath, and pretty soon you have to cut your rebates back. And it's hard for industry to plan when the financial incentives and rewards are not constant. So if you're getting involved in any of the renewable energy fields, you have to really be aware and take account of the risk, because it's so policy driven. And fortunately, it looks like the federal tax credit for PV is going to be with us for a while. I think that's fairly well established. Our state level incentive program has diminished from $350 a watt, installed watt, $350 rebate, to something like 65 cents now. It was intended to provide a decreasing rebate over a 10-year period to encourage the start of solar production and its installation, and help people get past the early phases when PV modules were expensive. And what we've seen actually is that PV modules have dropped in cost so much that even now, if the rebates went away altogether, it would still be relatively inexpensive to put in PV modules, even without a rebate, just because of the normal drop of costs. Under the current administration, there's been a pretty big increase in federal funding for PV and other forms of renewable energy. It's not huge, but it's a lot better than it was. There's a shift in the rebate programs from towards production-based incentives rather than an upfront incentive. So the California Solar Initiative program that I was kind of alluding to a minute ago would give you a certain payment per watt up front to install a certain size system. And that's now being considered to be not a really terrific way to motivate people, because there's no incentive for you to keep the system clean and running and well maintained. So now we're moving towards production-based incentives where you get so many dollars per watt that you generate and send to the utility. There are a lot more manufacturers of PV modules now than there ever were before. There are a lot of them in China. In fact, China is the leading manufacturer of PV modules now. What that's caused is for the PV modules to be really cheap, $2 a watt, to be commodities like jelly beans. You know, like when cell phones first came out, they were really, really expensive because there were only a few of them that took PhDs to assemble them, hunched over workbenches. But they've gone through that phase with PV modules now, and you can buy an entire PV module factory. You just write a big check, really big check, and this company comes and puts in this 1 square block PV factory, and in about 2 years you're cranking out PV cells. And this is happening in China like mad, and a number of other countries, and the cost is just going through the floor. So PV manufacturers are finding that they have to vertically integrate. They need to offer other services like design and installation and maintenance in order to reap the profits that are available in PV. Yes?
How much would it cost to actually power your house by PV?
You can figure about $6 or $7 an installed watt. So if it was a $2,000 system, what would that be? 6 times 2, 12 to $15,000, something like that. Depends on the type of modules you wanted, and then you get a third of that back from your tax credit.
And if you were to install one of these, how much time do you think it would take before it paid itself off?
There are 2 kinds of payoff. One is economic, and the other one is energy. And if you're an environmentalist, you probably are more passionate about the energy payback than you are about the economic. But the energy payback has gone from about 5 to 7 years down to just over 2 years now. So in almost no time at all, you paid back all the energy that went into the aluminum, the silicon, the labor, the trucks that came into your house. But from a financial standpoint, it depends on how you use it. If you have a hot tub and a electrically heated swimming pool, and you heat your house with electricity and things like that, you probably have this ridiculously high astronomical electric rate, and you're probably paying 45 or 48 cents for your top category of kilowatt hours. So for people like that, it's a no-brainer to put in solar electric systems. If you just get out of the top bracket, just get yourself out of the top bracket, you pay for it in 5 years. If you're like us, and myself, we are baseline electric use. We just don't need very much, and we conserve. So it would take us probably 20 years to pay it off.
Yeah.
So people like us would do it because, and we haven't done it yet, but we have a really old roof that'll need to go sometime, and then we probably will. But we would do it just for general principles, but not for economic reasons. And it turns out a lot of people are making that decision just on general principles.
Yeah, did you say that on your website, Solmetric website, there is a calculator or something? Could you please tell us about it?
A
Calculator?
calculator. There's that map, that contour map that we showed you earlier, that shows you which way you should point your PV modules.
Right.
And we also developed some software which we're selling now. It's a $400 a year license that designs your whole PV system. It's one screen on your computer. And that's probably what you're referring to. And that can be tried for free for 30 days if you ever want to do that on our website. So I want to get on to jobs because there's a few more comments about trends in the industry. Let's see if any of these relate to jobs, and I'll touch on those. Increasing number of utility projects, I think I mentioned that. Okay, so let's get on to jobs. 2 slides on this and then we're done, okay? First, renewable energy is one of the few industries that's really growing right now. And PV is certainly right in there with the other renewables. Solar thermal, solar PV, what do they call that, where you take corn and make it into ethanol? Things like a lot of different things. Biotech jobs where people are trying to get bugs to turn weeds into ethanol, or old newspapers. Yesterday at a conference I was at, there was a panel, and one of the panelists in the discussion was from a job, her company found jobs for people, and she was for people who were looking for renewable energy jobs. And she said, are there green jobs out there? Well, maybe not, but the green sector certainly has jobs. And what I mean by that is that green jobs probably carries more baggage or means more to us than it should. They're really traditional jobs, traditional disciplines like electrical engineering, mechanical engineering, thermal design, finance, accounting, all sorts of traditional jobs, just doing the same old thing but focused in a different direction. So you don't necessarily have to get a degree in PV in order to participate in the PV industry. And she said that hiring is taking place in all of these disciplines right now, but it's not as much hiring as you'd think. Like I mentioned earlier, we're in a place on the growth of renewable energy, which looks amazing because it's right at the top of the chart in 2010. But where we need to go is way up here. And so a few years from now, just change the label of the year and this graphs will look the same, but we still won't be where we want to be. So I guess what I'm saying is we're still at the infancy of renewable energy in all of its different forms. And we have an enormous amount of growth ahead of us. The downside of that for now, for getting jobs, is that there just aren't a huge number of them in renewables yet. But if you have a passion for doing it, you can find them. A young man just joined our organization after interning with us last year, before his last year in college. So he got to know us, we got to know him, everybody got kind of happy with each other, and then when we needed somebody, it was a perfect fit. I'll say more about that sort of thing later. There are some new roles in energy auditing, consulting, energy retrofitting of buildings, including really big buildings where you need mechanical and control system engineers and electrical engineers that really know their stuff to go in there and say, you can replace this machine with this machine and it'll save you this much energy, and do all the contracting and make it happen. So if you come from a background where you like to do things with your hands, you like to make things happen, that's a really great field. Tons of PV and renewable energy startups in the industry, especially in the Bay Area. And then finally, there are many applicants for every job, like I said. The guidance counselor that we talked with that talked in this panel said that the average educational level coming in the door to their agency looking for a job was a master's degree. That was the average, and we all went, oh, jeez. We were thinking back to when we were that age, and did we have a master's degree, and what's that all about? But I think that has to be taken with a grain of salt because the economy is so bad now that a lot of people are just staying in school another year and getting a master's degree. So, but I don't put too much stock in that. It's scary at the outset, but if you hang around with people that are in the industry, maybe do some informational interviews, get an interview with somebody who's in PV, and ask them what their job is like. You're not pitching employment, you're not looking for a job, you tell them that right up front. But just say, I'd like to talk with you and find out, what it's like so that I can make some career plans. You might even be able to arrange to job shadow somebody. Just follow them around for a day and find out what their job is like. Just